So far we have learned a very big category of uh, control charts called Shewhart control charts, right? These are X bar and R control chart, X bar and S control chart. And we also looked into individual measurement and MR chart, moving range chart, right? And one of the things that we studied while looking at these charts was how to calculate average run length, right? ARL1, when the process goes out of control. So let's actually go back and look at how we calculate ARL1, all right? So if you remember, ARL1 is nothing but it is equal to 1 by 1 minus beta, right? And we already have the formula for beta. So let's calculate ARL1 for a couple of values, different values of n, given that the mean shift is 0.5 sigma, right? So you're given that delta is equal to 0.5 sigma naught. And alpha is 0.0027. So automatically your Z alpha by 2, this is equal to 3, right? Now this is very standard. All of you have done this multiple times. So let's quickly go through this. For n equals to 2, beta will be equal to phi 3 minus delta is 0.5 sigma naught. So this is 0.5, and then sigma naught gets cancelled from numerator and denominator. And the value of n is 2. So this is square root of 2, right? And then minus phi of minus 3 minus 0.5 square root of 2. Now you are familiar that the second term is close to 0 because this is a very negative term. So we will approximately write this as phi of 3 minus 0.5 square root of 2. Now if you calculate, let me just do a quick rearrange here. If you calculate this value, you will get 0.99, which means your ARL1 is 1 by 1 minus 0.99, which is 0.01, which is approximately equal to 100, right? Does anyone have any questions on this one? Okay, so let's use the similar approach and see what will be the value of ARL1 for n equals to 5. Right, so again, we calculate beta equals to phi of 3 minus 0.5 square root of 5. Again, let's ignore the second term because it is highly negative. So it will be close to 0. And if we just have this term, we can write this as approximately phi of 1.88. And this will be equal to 0.97. So in this case, your ARL1 is equal to 1 by 1 minus 0.97, which is approximately equal to 33.33. Similarly, for the last case, you will get beta equals to capital phi 1.42, and your ARL1 is equal to 12.82. So you'll see that there is a trend here. There's a very clear trend here. As the value of n increases, your ARL1 decreases, right? So the trend here is as n increases, ARL1 decreases. Now, if you observe here, even though you're taking 10 different samples for each observation, your ARL is still 13. It is still a lot. In order to detect the change here, you still have to take an additional of 13 different samples, right? So what happens is for a shift in the process mean of mu minus mu naught, probability of type 2 error decreases with sample size n, right? And ARL1 also decreases. This is one information we have on Shewhart control charts, right? In fact, when sample size n increases, both alpha error and beta error, both of them decreases. Now, when alpha error decreases, ARL0 gets larger because ARL0 is 1 by alpha, right? So if alpha decreases, ARL0 gets larger, while ARL1 gets smaller because ARL1 is equal to 1 by 1 minus beta, right? And we know this, right? We know that we want ARL0 to be as large as possible, and we want ARL1 to be as small as possible. But to get this small ARL0 and large ARL0 and small ARL1, we have to take lots of measurements, right? We have to increase the sample size n. Now, the problem with increasing sample size is that it will delay the detection of a change. Why? Because if you want to have more measurements, you'll have to spend more time in collecting those measurements, right? So that will delay your detection. Also, when you take measurements, it will also increase the cost, right? So although we can increase n and get a very large value of ARL0 and get a very small value of ARL1, it will actually increase the detection time because it takes a lot of time to collect samples. And it will also increase the cost, overall cost of the change point detection, right? Now, one reason why Shewhart control charts do not work very well is that because they don't have any memory. Now, I'll talk about what memory is. If you look at any control chart that we have learned so far, what we do is we have a center line, call this CL. We have upper control limit, we have lower control limit. What you do so far is as soon as you have an observation, you just plot that value here. So if you have observations x1, x2, x3, x4, you just take these values and you start plotting these values, right? x1, x2, x3, x4. You keep on plotting these values. When we plot x4, we don't care what the value of x3 was, right? Again, when we plot x3, we don't care what the value of x2 was. And similarly, when we plotted x2, we didn't care what the value of x1 was. We just plotted these values as we obtained these values, right? That's called having no memory. I am just independently plotting down these values as I am observing these values, right? So it says that a Shewhart chart always uses the latest update of process measurements instead of utilizing the information embedded in the entire sequence of measurements. And this is called no memory process. Okay. I'll just give you a quick example here. I have some samples, sample 1 to sample 30. And I know that for this particular data, mu is equal to 10 and sigma is equal to 1. I already know these values. So if I know these values, I can construct a control chart, right? My center line will be 10. My upper control limit will be 10 plus 3 sigma. Sigma is 1, so it will be 1. And this will be 13, right? And similarly, LCL will be equal to 10 minus 3 times 1. It will be equal to 7. So I've used these values here and I've plotted this control chart. And after plotting the control chart, I have just put down the values like a regular control chart, right? So the first value is 9.45. This is 9.45. This is 7.99. And this is 10.52. 10.52, 7.99, and 9.45, right? This is what means it to be having no memory. All right, now let's do a quick modification here. Okay, we'll do a quick trick here. Let's draw another column here, and let's call this column B. What we will do is in the first step, we will subtract the mean value from each of these observations. This is straightforward, right? we can just subtract the measurements from each of these values. So I know mu is equal to 10. So the first value will be 9.45 minus 10, which is minus 0.55. Second is 7.99. So 7.99 minus 10 is minus 2.01. And similarly, I can keep on writing these values, right? Minus 0.71, 1.66, 2.16. Right? And I can keep on doing this until the last sample, which will be 0.52. So I've done a very quick change here. I have just subtracted the mean from all of these observations, right? Now let's do another thing here. Let's write another column, column C. For this column, what I'm going to do is I'm going to define each value and I'm going to call it as C1, CI. And CI is nothing but xi minus 10, which is the column B, plus CI minus 1. And I'm going to say that C0 is equal to 0. So let's see what happens. If C0 equals to 0, then C1, I equals to 1. This is nothing but minus 0.55 because C0 is 0, right? Now, once I have C1, I will write C2 as xi minus 10, which is minus 2.01 plus ci minus 1, which is C1. So this is minus 0.55, and this value will be equal to minus 2.56, right? Similarly, I can write down C3 equals to minus 0.71 plus minus 2.56, which is C2, and this gives us minus 3.27. Any questions so far on this one? Any questions on the calculations? All right, so once we are able to finalize this, we can write down C1, C2, C3, C4, up until C30. We all can write this, right? Just using the straightforward formula. Now, once you calculate these values, C1 up to C30, let's actually plot these values and see how it looks like. So when you plot these values from C1 up to C30, you'll notice something very interesting here. You will notice that when I plot the values of CI, my plot started to deviate from a center value at around 21. So this is sample number 21. So at around sample number 21, your chart starts to indicate that something has gone wrong, right? Right around this point. And in fact, there was actually a change in the process mean done at sample number 21. Now, if you go back to the regular control chart, which is the Shewhart control chart, it's almost impossible to tell if anything happened at this point, right? Because all of the points are still within the control limits and you are not able to detect anything. Now, the primary reason why you're not able to detect anything in the Shewhart control chart is because if you calculate ARL1 for this process, let's do a quick calculation, right? The shift in the process mean here is, if you go to this sample, the shift in the process mean is from 10, mu equals to 10 to mu equals to 11, right? So the shift in the process mean is just 1. And I think sigma is equal to 1 for this process. So if you calculate ARL1, it is, sorry, if you calculate beta, let's calculate beta first. Beta equals to phi of 3 minus 1, and then n is 1. So square root of 1 divided by sigma, which is also 1. So you will get phi equals to 2. Just to simplify the calculation, I have ignored the second term here. I hope you see that, right? So if you calculate beta for this, you will get 0.98. And if you calculate ARL1 for this process, you will get 1 by 0.02, which is 50. So what it tells is, if you want to detect a change by using this Shewhart control chart, you will have to collect 50 additional observations. You have to take 50 additional measurements after 21. After 21, you have to make 50 additional measurements to detect this change. Now, when I use slightly modified form, you can see that I'm able to at least visualize a change pretty soon, right? After just one or two observations, this and this observation, I'm able to visualize that something is wrong. It means something has changed. So this was a very kind of vague explanation of how we can modify our control charts to bring in the memory of the process. If you didn't observe, CI here is acting as the memory. Every observation CI is the current measurement xi minus 10 plus CI minus 1, which is the history of the process, right? So by including the memory of the process, we are able to do much more better. We are able to much efficiently detect the change as compared to the Shewhart control charts. Right, so this is just a very brief introduction. We'll formally talk about what this method really is, right? So what we have done here is, by considering previous samples, that is letting a chart to have memory, a chart can achieve faster detection of small mean shifts. If there is a very small mean shift, like 1 sigma or 0.5 sigma, we can detect those changes very fast. And there are primarily two methods. Actually, there are lots of methods that use memory, but the two of the most fundamental methods were CUSUM chart, which is cumulative sum, and EWMA, which is exponentially weighted moving average. These methods were developed around, I think, 1940s, or not 1940s, but I think 1950s and 1960s, late 1950s, 1960s. And after that, uh, a lot of researchers have been working on this domain of change point detection, detecting when the process mean changes. And as some of you are already downloading papers and reading papers, you will all see that somewhere they will mention about CUSUM or EWMA, or some kind of variant of CUSUM or some variant of EWMA. In fact, let's say if you're developing a new method for detecting the change point, it is always recommended that you compare your method with CUSUM and EWMA. So when you start reading your papers, you will see that when they present their case studies or when they present their results, they will always compare their performance with that of CUSUM and EWMA. So what I want to say here is, CUSUM and EWMA are two of the most fundamental methods that incorporate the memory of the process. All right, any questions so far? Okay, so let's formally talk about CUSUM. What we did so far was actually CUSUM, but we'll talk a little bit more formally as to how to develop a CUSUM control chart. Just some brief history here. CUSUM method was first proposed by Page in 1954 and then later revised in 1961. So to study CUSUM chart, let's try to set up some variables here, okay? Let's say x1, x2, x3, ... These are our observations, okay? Let's say mu naught is in control process mean. And when the process mean changes, let's call it mu1. Mu1 will be our out of control process mean. And let's also define the standard deviation. Let's call this as sigma naught. This is the standard deviation of our observations, which are our x's, right? Now, in the example that we saw here, we only had n equals to 1, right? For each sample, we have only one observation. So in this lecture, we will focus on n equals to 1. All right, so we will focus on n equals to 1. But if you have n greater than 1, we can construct CUSUM chart for x bar. You all remember how to calculate x bar, right? X bar was equal to summation of x, actually x bar I, to be very precise. X bar I is equal to x ij, j equals to 1 to n, 1 by n. This was xi bar, right? So we can calculate xi bar, and in a very similar way, we will construct our control chart if n is 1. But just to keep it simple, we will focus on n equals to 1. Okay. Now let's write down a general model for control chart, the one that we just saw, right? Model for a control chart is, we define it by CI, and we say that CI is defined as summation of xj minus mu naught. Mu naught is the in control process mean, and then you sum from j equals to 1 to I. Now, just to keep in mind, whenever I write this symbol means defined as. Okay. Now let's break this down. If we can rewrite this as xi minus mu naught plus sum of xj minus mu naught, j equals to 1 to I minus 1. So I've taken one term, the last term from the sequence. Okay. So now you can write this as xi minus mu naught plus, this is nothing but ci minus 1. And this is exactly what we did in the example, right? This term is called your current observation. This is your current observation, right? This is your current observation. And ci minus 1, this is called memory or history, whatever term you want to use. So again, observe, ci for any sample I is nothing but xi minus mu naught, which is your current observation, plus ci minus 1, which is the memory. Right, so this is a very general model for CUSUM chart. Now, when we actually implement CUSUM chart in practical applications, it is slightly different than this one, right? And I'm going to talk about that in a moment, why it is slightly different than this one. But one of the major reasons why we want to have this general model is because it helps us understand the behavior of control chart. So this is not a standard formulation, but it helps in understanding the behavior of CUSUM chart, right? So we will see what is a standard formulation in a little bit, but for now, let's try to understand the behavior of a CUSUM chart, how a CUSUM chart would behave under different circumstances, okay? So we have this general expression, Ci equals to Ci minus 1 plus Xi minus mu naught. Actually put this in bracket so it will make more sense, right? Now, if we have this, we can always write down expected value of Ci equals to expected value of Ci minus 1 plus expected value of Xi minus mu naught, right? And I can write this as further as expected value of Ci minus 1 plus mu I minus mu naught, where I'm saying that expected value of Xi is equal to mu I. I'm just saying that at sample I, let's call the mean to be mu I, okay? And let's call this as current mean. And we already know that mu is our in control process mean, right? Nothing fancy. I've just taken the expected value of Ci and I have written down in terms of the expected value of Ci minus 1, the current mean, and the in control process mean, right? Now let's see what are the possible scenarios that can happen. The first case is if there is no mean shift, okay? The process remains in control and there's no mean shift. If there's no mean shift, mu I will be equal to mu naught, and I can write down expected value of Ci equals to expected value of Ci minus 1 plus mu naught minus mu naught, right? And this will be equal to expected value of Ci minus 1. So if there's no change in the process mean, if there's no mean shift, there is no change in Ci, right? The expectation of Ci and Ci minus 1, they are both same. Now, the second case is your current mean, which is mu I, can be greater than mu naught, right? This is the case when there is an upward shift, the mean increases, right? In this case, what happens is expected value of Ci is equal to expected value of Ci minus 1 plus mu I minus mu naught. Since mu I is greater than mu naught, I can say that expected value of Ci is greater than expected value of Ci minus 1, right? In this case, what happens is Ci will start to drift upwards. This was the case that we looked a few minutes ago. If you go back to the previous example, notice here that your in control process mean is mu equals to 10 and your process mean after the shift is 11, right? So your mu I is greater than mu naught. And when this happens, the chart for Ci will start to drift upwards, right? Drift upwards. Make sense? Okay, so the third case is when mu I is less than mu naught. That is, your new process mean is smaller than your previous process, your in control process mean, right? And when this happens, your expected value of Ci is equal to expected value of Ci minus 1 plus mu I minus mu naught. In this case, mu I is less than mu naught, so I can write down expected value of Ci, expected value of Ci is less than expected value of Ci minus 1, right? And in this case, your Ci will drift downwards. All right, any questions? Right? So this is what I was referring as the behavior of CUSUM chart. There are three different characteristics that you can observe in a CUSUM chart. First is if there is no process, if there's no mean shift, your CUSUM chart will stay stagnant. Okay. If there is an increase in the process mean, the CUSUM chart will start to drift upwards. And if there is a decrease in the process mean, your CUSUM chart will start to drift downwards, right? So there are three different scenarios here. Now I have I'm just highlighting this again. I'm just contrasting the Shewhart chart and the CUSUM chart again here, just for your reference. This is the case when mu I is greater than mu naught, and you can see an upward drift here, right? Now, I told you that we don't generally use this CUSUM chart model in practice, right? One of the primary reasons why we don't use this general model for in practice is because although I have the control chart, I don't have the control limits, right? You see here, right? We only know what to plot in a control chart, but we don't know what are the control chart limits. So that's when we do some modifications to this general model to come up with a standard formulation of CUSUM control chart. So standard formulation of CUSUM statistic is not that different from what we have studied right now. A standard CUSUM statistic actually takes care of both the two cases, the upward shift and the downward shift. So if there is a increase in the process mean, we will use Ci plus. Remember, plus is for increase in process mean. If there is an increase in process mean, we will use Ci plus, and that is equal to maximum of 0, comma, Ci minus 1, again plus Xi minus mu naught plus K. And this is also called upper CUSUM chart, right? This is when there's an increase in the process mean. And similarly, if there is a decrease in the process mean, that's when we use Ci minus. Minus is for, let's actually write this as C plus and C minus. So C minus is when there is a decrease in process mean. Right? And then this is called a lower CUSUM chart. And again, just like the previous case where C0 was 0, we will have here C plus as well as C minus 0 equals to 0. Okay. This is how you initialize the control chart. This is how you initialize the CUSUM control chart. Right now, there is one parameter here, parameter K. And K is a user specified constant. And in the next couple of slides, we'll see how we can determine this value of K. Okay. Now, I have Ci plus and I have Ci minus, but I still don't have my control limits, right? So hang on. In order to construct a CUSUM chart, we have to first of all select the value of K, which is the parameter here. And we have to select a decision interval, which is minus h to h. This is our control limit. And the way decision is made is the process goes out of control if Ci plus is greater than H or Ci minus is less than H. So if Ci plus is greater than H, we will conclude that there is an upward shift, right? And if Ci minus is less than minus of H, then we will conclude that there is a downward shift. Okay, so this is how we define control limits. Now let's try to answer the question, how do we determine the value of K and how do we determine the value of H? Okay. So before we do that, let's try to understand what we just did. First question that you might ask as to why we want to have Ci plus and Ci minus instead of just Ci. A simple question to answer this is, to this question is, we want to decouple the positive and the negative mean shifts. So if there's a positive mean shifts, your control chart will start to shift upwards. This is when you have a positive mean shift. And if you have a negative mean shift, your control chart will start to drift downwards. Okay, so you want to decouple these two effects. That's the most important reason to have Ci plus and Ci minus. Now the second question is, why do we want to have K? Now to understand the meaning of K, let's try to first of all appreciate the fact that there is always some kind of fluctuation in the measurements that you make, right? We have seen this since the beginning. Whenever you take measurements, there's always some kind of fluctuations in the measurements. And these fluctuations can happen due to some kind of assignable cause. Sometimes it can happen because of some kind of unknown factors. Sometimes it can happen because of measurement error, right? The device that you're using to do measurements. So what K does here is, if your true mean is mu naught, okay? Let's say your true mean is mu naught, but because of fluctuations, your value of mean stays between mu naught plus K and mu naught minus K, all right? If your actual mean stays between mu naught plus K and mu naught minus K, then this parameter K will provide robustness against small fluctuations, all right? So in other words, if we don't have this parameter K, what will happen is the small fluctuations in the process will add up together and will show you a drift upwards or downwards, even though there is no change in the process mean, right? So it's kind of like a safeguard threshold. Safeguard threshold. So that's the meaning behind K. Now let's see how we can estimate the values of K and H. The first, now before I go and talk about how we estimate the values of K and H, I want to let you know that estimating the values of K and H is still an open question. So if some of you are reading papers, something closely related to this might be an opportunity for you to maybe think of a method as to how to select the values of K and H. So far, there are some, recommended methods. They're also called rule of thumb. Sometimes people use lots and lots of simulations and data sets to estimate the value of K and H. But so far, there is no kind of like a standard method to select the values of K and H, right? If you read different papers, you will always find that people will have different methods of estimating the values of K and H. So what I will do is, first I will talk about a recommended method, so-called rule of thumb, and then I will talk about one of the methods that has been proposed in literature not too long ago. Okay. So the rule of thumb is to choose K halfway between mu naught and the out of control value mu1. What it means is we want to select k as mu1 minus mu naught divided by 2. Okay. Now you might start thinking that, well, in order to find out the value of k, I need to know mu1 as well. But in most real world scenarios, you will not have the value of mu1. You will actually not know what is the out of control process mean, right? So for this, for rule of thumb, what you do is you just make an assumption. Okay, you make an assumption that mu1 is 2 standard deviation away from mu naught or 1 standard deviations away from mu naught, right? So you make some assumptions here, and once you have an out of control value of mu1, you can write down k as absolute value of mu1 minus mu naught divided by 2. Make sense? Um, to give you some examples here, let's say if mu1 is equal to, I don't know, mu naught plus 2 sigma. So, no, let's actually say 1 sigma, because that's the example we will solve right now. So you have k is equal to 1 sigma by 2, which is equal to 0.5 sigma. Okay, that's how you define k. And h is typically chosen to be 5 sigma. Again, this is ad hoc rule of thumb. We're just saying that h is equal to 5 sigma. Now you might wonder how we get these values. The simple answer to that question is people have been doing research for 50, 60 years. And when they do research, they always solve a problem, right? When you solve a problem, you see what is the most typical value of these parameters. And with years and years of practice, people have proposed some recommended values. That's it. There's no scientific evidence behind this as to why you should choose k as mu1 minus mu naught by 2 or h as 5 sigma. These are just recommended values. So take these values with a little grain of salt. All right, so now we have k and we have h. All right, any questions so far? Now, just to give you some more insights here, when you construct your CUSUM control chart for CI plus, if you go back to the formula, CI plus is max of 0 comma the big term here, right? So you can see here that this value of CI plus will always be greater than 0. Does everybody see this? It's max of 0 comma the second term, right? And the value of CI minus will always be negative. It is minimum of 0 comma this whole term, right? So what happens is when you construct your control chart, let's say you construct your control chart for CI plus, it will have a minimum value of 0, and then you will start to plot here CI. Okay. And this is where you will have your 5 sigma, which is your control limit. And similarly, if you are making a control chart for CI minus, your maximum value will be 0, and your control chart will plot below this, and whenever the change happens, it will start to drift. And this is somewhere you will have your minus 5 sigma. Make sense? All right, let's solve a quick question here.